says, hey, welcome, that we're using Green's theorem to evaluate this. Number 9, we have a circle. And so give me a sec. Do I really need to? Yes, I do. Let me copy this and put it down at the bottom so that I can write. Here we are. So let me just cram it down here. Come on. Okay. So first things first, we have this circle. So we have this. We're dealing with this circular path. So going around, and I think we're supposed to be going counterclockwise. So let's just assume that this is counterclockwise. Using Green's theorem, we can set this up as a double integral instead of using this the curve here, since this is a simply connected region. And I'm going to convert to polar coordinates, as you might guess. But before I do that, I'm going to first of all write this in rectangular coordinates. I'll just call this the region R, and I'll put dA over here. We'll deal with the conversion to polar in just a minute. So just to remind you, you take the thing that is the y coordinate, if you will, and you do the derivative with respect to x. So I have 3x squared negative, and then you subtract off the thing that is the x coordinate in the vector field. And I know it's kind of masked here with the dx and dy, but that's the x coordinate for the vector field, and you get 3y squared. You do the derivative with the y, with respect to y, and then subtract. So I do the derivative of this, subtract that. So far, so good. So now that we've got this, hopefully it's pretty obvious to you what's going to happen is that this thing is going to be just negative 3 times x squared plus y squared. So I'm going to just convert that to r squared. So here's the not the final answer, but at least the integral that you're going to use. So this is converting to polar form. Polar. Don't forget to put the extra r in there. And then I've got negative 3r squared coming from this. dr d theta. And r goes from 0 to 2, and theta goes from 0 to 2 pi. Easy enough that you might be able to do this without much work. Let me see if I can. It's going to be r to the 4th over 4. We're going from 0 to 2. So what's that going to be? 3 times 16 over 4, so 12. So negative 24 pi, is that the answer? Hey, look at that. So it is simple enough. And once you have it set up, especially when you turn to change it to polar coordinates, makes it super easy. But that's that one. Does anyone have any questions more about this? I mean, I glossed over this step here, but I'm guessing that you can do integrals of basic polynomials. So you're all right now, Matthew? Excellent. Were there any others that caused a little bit of grief or consternation? All right, well, let's take a look at this quiz. As I mentioned yesterday, since I can't get myself straightened out, I'm going to just give you the quizzes like this. So you can do it. We'll go over it. It's kind of like the day before an exam. You know how to collect the quizzes. That way you'll have a chance to study for them. So go ahead and take a look at this, see how much you can get done, and then we'll work it out together. It's not too bad, though. Very similar to what, well, there's no polar coordinates on this one, though. Guess I should do it too. Please. Some of you look like you're finished. So I'll give you another 30 seconds just in case you're trying to polish off this problem. It wasn't too bad though, was it? All right, now we can play our game, which seems to be a recurring game of Find My Mistake. So hopefully I didn't make any, but you never know. So let's get started. So the first thing is to set this thing up with the derivative of the y coordinate from the vector field. And that's this with respect to x. And then the derivative of the x coordinate from the vector field with respect to y. So I subtract this minus this. So far, so good. And my limits are just directly from this region, nice rectangular region. I guess it's a square. So we always love that because you have constant limits. Then I did my antiderivative. Hopefully I got it right. Y squared over 2. These things are in doubt these days, I guess. And xy this is with respect to y first. And I'm plugging in, I probably should have labeled those as y. Y equals 1 and y equals 5. So far, so good? Okay, now let's go ahead and plug in the numbers. And now here's where things get a little shaky because I did the calculations in my head. So when you plug in 5, you get negative 25 halves. And when you plug in 1, you get negative 1 half. And I subtracted those in my head and got negative 24 halves, which is 12. And then I did the same thing here, negative 5x minus negative 1x, which gives me negative 4x. Did I do okay? Like I said, things haven't been going well lately, so with my mental arithmetic, so you'll have to keep me straight here. Then I'm going to do the antiderivative of that. Hopefully I got that one right. This one's straightforward, nice polynomial. I'm going to plug in my limits. Here again, I kind of did it all in my head. Is it negative 80? All right, I got one right. That's exciting. Okay, good. So negative 80, if you got it right, put a star at the top, put an A plus 100%. I'm just going to assume you all got it right so that when I go to do this, I'm just going to say yes, 100%, A plus, A plus. Okay, let us move on. Ooh, I don't have this set up. Let me just, that's not for you. Let's move back, get this here. We're coming down the home stretch. Just a couple of things left. Does this look good? Yes, it does. And so the first thing is curl and divergence. I heard some of you talking about fluid dynamics. This is the application that involves this idea of fluid dynamics. We're going to talk about what curl is in just a minute. So we'll do curl first, and then we'll do divergence. They're both pretty simple, easy to compute. So curl, first of all, let's talk about how to compute it, and then we'll talk about what it means. So first of all, how do you compute this thing? Well, we have to use this operator, this gradient operator of sorts. It's a what is that symbol? Nambla? Whatever that is, the upside down delta. That one, so you take that of f. This is a function, so this is not a vector field. So normally we think of that as being a vector field, right? But this is going to be the sort of the gradient operator. And the way that this operator works is we're going to just take the partial derivative of each of the whatever it is that we're going to pump into this. So just like the gradient, we're going to take the derivative, if you will, for each of those and make a sort of a gradient out of this. You might think, well, that is the gradient, but we're going to use this in a little bit different way. We're going to use this as if it were an operator to help us solve some problems. And so curl is, so this is what this operator is. Sorry, I should have said, there it is. That's the operator, the gradient operator, if you will. Notice that I don't have an f here. And that's because we're gonna have to plug in the f depending on what function we're evaluating. Okay, so you have that, and then what we're going to do is we're going to do the cross product of this operator with a vector field. So that's why you're going to take this thing that you're familiar with, this gradient, but we're going to apply it in this weird way. So if you take the cross product of this with our vector field, then you get this thing that we call curl. So the curl is just this gradient operator crossed with the vector field. It'll be a lot easier once we actually see how this is done. But if you don't like this, so this is the way that I think of it. It's easiest for me to sort of see the pattern. You could also just write this way down here, but I find that to be a lot more complicated because it's a lot to memorize or to keep track of. This is nice and regular. So that's the way I'm going to do it, using that cross product version. This is just the cross product, by the way, down here. Okay, so let's see how this is done so that we can actually do this. So the first thing, oh, well, look, it all showed up at once, didn't it? So let's say that I have this vector field, and it's a three-dimensional vector field. We'll explain why in a bit. And I want to find the curl of this vector field. So I'll do this, set this up. So it's the cross product of this. So you've got the derivatives, x, y, and z. And then you have the x, y, and z from the vector field down here. And then I just have to set up this do the cross product. Cross product isn't too bad with this one. So give me a sec. And I'm going to pull this over to my other app because I don't like this doing it in, there we go. Yeah, doing it in PowerPoint is kind of painful. There. So there's the start. And so just, this just gives me sort of a help in order to keep myself straight. So this is the partial with respect to x. This will be the partial with respect to y. Just like with your cross product, I'm just going to copy the two first columns down to help me do this cross product. Okay, so let's set up our down arrows. And so notice that once you've got this way, you can think of it this way. You have I times the derivative with respect to y of this thing. And then you do j times the derivative with respect to z of this thing. So you're just going down the diagonals and copying down what it says. So the first one is going to be I times negative 2y. And then I add to this j times x, because that's the derivative with respect to z of this thing. And then we can just get you guys involved as much as we can. So let me randomize. And we'll get Cooper-Claggett. What's the derivative with respect to, what are we on? X. Derivative with respect to x of that thing. YZ. Yeah, so that one's going to be k times yz. Very good. Now we'll do the up arrows. So, and you might have a better way of doing this or a different way, and that's fine. Now the only problem with the up arrows is that you have to kind of read backwards. This will be k times the derivative with respect to y of that thing. So Daniel, what's the derivative with respect to y of that first component there? 0. Oh, it is 0. So I'm going to write it down, though, just to emphasize k times 0. And then this next one is going to be I times the derivative with respect to z of that thing, that x, y, z. Christopher, what's the derivative with respect to z of x, y, z? Very good. So I times xy, and these are all going to be minus, 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 because they're the up arrows. And then finally, we need to do j times the derivative with respect to x of that thing. So Ryan, what's the derivative with respect to x of this? 0. It's also 0, yeah, so that's nice. Makes things easy for us. I guess I've written that backwards, but whatever. 0 times j, same thing. So let's collect all this stuff together. I'll put it down here. So the curl of f is going to be I times, let's see, it's going to be negative 2y minus xy times I. Looks like j is just going to be x times j, and then yz times k. So there's the curl of this particular vector field. And of course, we would be interested in the curl at specific points. I'll show you a picture here in a minute. But if you had a particular point, for example, the point 1, 1, 1, I would plug 1, 1, 1 into here for x, y, and z, and I would get negative 3i plus j plus k, and that's a vector. And so it'd be nice to know what that vector means in terms of your vector field. So that's the next step, is to figure out what this all means. So, oh, well, we'll come back to that in a minute. So here's what you're going to find with vector fields, is that the curl is, it kind of describes, the word kind of evokes this idea of movement, curling, moving around. And so if you have a point x, y, z, like the point 1, 1, 1, and you find the curl for that particular point in your vector field, it's going to be a vector. And it turns out that using the right-hand rule, of course, the motion, you'll find that in general, the vectors in that vector field are moving around in this direction in that plane. If you just sort of look at that sort of local area here. Now, of course, you're not going to find circular vectors. Like, the vectors aren't going to be perfect circles like this, but this is the general motion. That this is the, if you think of the various arrows that you might see around this vector field, things are moving predominantly like that in the vector field. A couple other little tidbits about vector curl is that if you have a conservative vector field, then the curl will be 0. So curl is 0 for a conservative vector field, interestingly. And so that's one way to check to see if you have a conservative vector field, is just compute the curl and see if it's 0. If it is, then conservative. And you can apply, of course, once you know something's conservative, you can apply the fundamental theorem of line integrals, which is helpful. So there's at least 1 or 2 problems on the homework which ask you if a particular vector field is conservative, you would just compute the curl. And if it's 0, then you're all set. Let's see, vector field, all whose components are continuous. Yeah, okay, that's the same thing. That's the same theorem. Okay, thought that was different. All right, let's move on. So we've got curl. The other thing that we're going to learn about today is divergence. In divergence, if you understand how we compute curl, let me just jot it down up here. So just here's curl. Looks like this. You do this gradient operator crossed with your vector field. So that's the curl. The divergence, that is going to be the gradient operator dotted with the vector field. So that's kind of why I like this notation, the cross product for the curl, is because of the symmetry, if you will. I don't know. The fact that curl is the cross product, divergence is the dot product. Anyway, let's get to the actual definition and see what it means and how we compute it. So divergence, this is literally it for divergence. It's actually much simpler than curl, of course, because you just got these 3 things. But I'll write this like this, but I'll also show you this dot product in just a minute. So you just take the first component, do the derivative with respect to x, second component, do the derivative with respect to y, and the third component, do the derivative with respect to z. If my memory serves me correct, when you were doing this, either on a quiz or on a test, some of you actually did this, like errantly you did this incorrectly for whatever problem we were doing, but you were basically computing this divergence, whatever it is, which we'll explain what it is in a minute. So the other form, as I mentioned, the other form of this is this. The divergence is this gradient operator dot product with the vector field. And you can see that here, that the gradient operator is basically this. I'll write it down. So the gradient is this, and this, and this. And of course, your vector field is P, Q, and R. So you can see that if we just do a dot product, take this times this, this times this, and then this times this, you get exactly this divergence. All right, we're going to use the same exact vector field that we did just a minute ago, but we're going to compute the divergence for that vector field. And then we'll see what the divergence means. Whoops. So it's the same vector field. So I'm just going to switch over. I'm not going to bother copying and pasting. So it's the same thing here. And we're just going to compute the divergence for this thing. So let me just do this. Divergence of f is going to be the partial with respect to x of xz plus the partial with respect to y of xyz plus the partial with respect to z of negative y squared. Notice that the divergence is not a vector, it's a scalar. And like I said, we're going to have to explain what that scalar, what it means in just a minute. But this is just the way that we're going to compute it. Let's go through and get these three pieces. I don't know if this is, no, this isn't. Ah, interesting. So actually all of the things that we computed up here are partials with respect to y and z for this one, the partials with respect to x and z for that one, and the partials with respect to x and y for that one. So divergence, you're actually using the different partials than the curl. And I guess taken together, we use all 9 of the partials for this particular thing. But let's go ahead. We'll get our 3 partials. So Andrew, what is the partial with respect to x of xz? Very nice. And then Luke, what about the partial with respect to y of this xyz? Yeah, just xz. And then Tyler, what about partial with respect to z of that last thing? 0. It is 0. Very good. So there it is. So this becomes just, I guess you could write it like this, z times 1 plus x if you wanted, but that doesn't. So in a similar fashion to the curl, this thing actually does have some meaning. So here, we'll just explain the curl, whoops, cull, give me a sec, curl of f evaluated at 1, 1, 1, just to contrast the two, we said was negative 3i plus j plus k. So what that means is that at the point 1, 1, 1, if you have that vector, so here's the point 1, 1, 1, draw this picture again, I guess my arrow is not pointing in the correct direction. You'll just have to rotate your point of view so that it is pointing the right direction. But anyway, if that's pointing kind of up that direction, then that means that there is at least some motion. It's not going to be perfectly circular, but in general, things are kind of moving this way around this, if you look at that point in space. So that's the curl. Divergence, on the other hand, let me write that down. The divergence for f at the point 1, 1, 1 is going to be 1 times 1 plus 1, I guess, which is 2. And what that tells you is it tells you the tendency for stuff to move. So if you think of this as a fluid, and there's motion within the fluid, this is the tendency for things to sort of swirl around, the curl. Divergence is the tendency for things to move. So if this number is big, it means that we have a lot of motion moving, diverging from the initial space, whereas curl, it's just how much are we moving in a circular or close to circular. And of course, this, in reality, your vector field probably isn't going to have a circular situation there, but you might have something like this. Here we go, where the vectors, I'm trying to emphasize that it's not necessarily circular. You might have something where the motion is more elliptical or other weird shapes, triangular, I don't know. But you could have some sort of a, just that the motion is all going in a circular thing around that. This might not be the center of this. It could be over here. Like if that point is here, you'd still get a curl that was similar to this. Okay, let's see. Just a few more things, a few more theorems, and then we'll be all done. Then we'll be done a little bit early today. I guess we should talk a little bit about the final so that you know what to do. Okay, so if you have a vector field and continuous second order partial derivatives, then this will always be the case. If you take the divergence of the curl, you do get 0. So that's just a little interesting tidbit. So I guess we've already talked about this. If divergence is 0, then this function, so this is kind of interesting. This vector field is said to be incompressible. So if the divergence is 0, you don't have any motion. So it's the motion, if you want to think of it that way. You have a gas or a fluid moving maybe through a pipe or through whatever it is, through space. Let's see, anything else that we need to deal with here? If we do the divergence of a gradient vector field, then you get 0 always? Apparently you do. The divergence of a gradient vector field is apparently 0. So whatever, so there's that. We don't need to do this. Okay, so that's it. So we're winding down. Just to let you know what's going to happen as we go forward. So Wednesday we have a class where we're going to deal with some things. What is it? I think surfaces, some sort of surface, parametric surfaces or something, whatever the next section is. Friday, I'll give you the final and instructions for the final. But just to give you a quick preview, the final is going to be like on a piece of like, it'll be similar to your tests, only a little bit smaller, actually, oddly enough. But it's only because I only have the answers, like answer blanks, and you'll have to put your solutions on separate pieces of paper. I'll go over that, though, when I give it this to you Friday. But it is a take-home final, so there isn't a practice exam. And then that will be due during our final exam period next week, which is Wednesday. Is that right? Wednesday morning. Yeah, so I'll give you more instructions on exactly what to do, where to go, and how to do it when we get that. So a little bit short today. My apologies if you were looking for a little bit more stuff, but you can stick around and chat if you'd like to. Otherwise, hope you have a great day. Oh yeah, absolutely. I'll add it to the pile since Austin gave me his. I definitely want to keep it.